Welcome back to Heraverse. In today's video, NASA spacecraft targets 3IATLAS amid questions over its mission. We will calmly walk through what this object is, why a NASA spacecraft is watching it, and what might happen when it crosses Jupiter's domain. If you appreciate clear, slow-burn explorations of the unknown, please like the video, subscribe to Heraverse, and share it with friends who enjoy cosmic puzzles. Thank you for your time and your curiosity. On a cold January night in the year 2026, the flow of routine space telescope data delivers something that refuses to be routine. The calendar marks January 12th, and astronomers who have been following the strange interstellar visitor cataloged as 3IATLAS now see their quiet unease harden into a clear problem. New images, taken only a few days earlier on January 7th, arrive from the Hubble Space Telescope as a carefully processed composite, combining multiple exposures into a single, sharp view of the object drifting against the starfield. In that view, cutting through the faint haze of the coma, a feature stands out with a clarity that leaves little room for interpretation. From the nucleus of 3IATLAS extends a narrow, coherent structure pointing almost exactly toward the Sun. It is bright, sharply bounded, and oriented upstream against the flow of particles and light that pour outward from the star. In standard comet science, such a structure should not exist. For decades, comets have been understood as icy bodies that heat up as they approach the inner regions of the solar system. When sunlight strikes their surfaces, volatile ices turn directly from solid to gas, a process called sublimation. The escaping gas drags dust grains with it, building a diffuse atmosphere and forming tails. Those tails are shaped by two main agents. One is solar radiation pressure, the push of sunlight on dust particles, which tends to drive the smallest grains away from the star. The other is the solar wind, a stream of charged particles that flows outward, sweeping ionized gas and dust into long, graceful structures that always lean away from the sun. Every comet studied since the invention of the telescope has followed that simple rule. Material is pushed outward. Fine particles stream away from the star, never toward it. The tails bend back, never forward. 3IATLAS now appears to ignore this rule. The new imagery shows an anti-tail in an extreme and almost geometric form, a jet that runs straight into the oncoming radiation and wind, rather than being bent away. The structure stretches for an estimated hundreds of thousands of kilometers, on the order of the distance between Earth and its moon. Yet it does not break up into a diffuse plume. Instead, it holds as a long, narrow beam, many times longer than it is wide, maintaining a sharp profile where theory predicts turbulence and scattering. The first hints of such a sunward feature are present in data gathered in July of the year 2025, but at that stage, the evidence remains ambiguous. Some teams propose that the apparent sunward extension might be an illusion caused by viewing geometry, a projection effect in which a normal tail happens to line up along the observer's line of sight. Others suggest that subtle processing artifacts might have enhanced noise into the semblance of a jet. The cautious response is to wait for more data, for better geometry, for confirmation. The January sequence removes that caution. Multiple exposures from different nights, processed by different groups using independent methods, all show the same thing. A persistent, bright, sunward-pointing jet emerges from the region of the nucleus and holds its direction through the observing run. By the time the composited images circulate through research teams, the feature is no longer a rumor passed in quiet conversations, but a concrete pattern that must be explained. The usual escape routes of perspective tricks and software artifacts collapse under the weight of repeated measurement. What remains is the uncomfortable conclusion that 3IATLAS is expelling material directly against the combined forces of radiation pressure and solar wind, and that the outflow is strong and dense enough to resist being swept back. The brightness profile along the jet suggests that whatever is being launched from the nucleus is either unusually massive, unusually cohesive, or being replenished at an extraordinary rate. None of those options sits easily within simple models of a passive comet nucleus. As astronomers examine the time series, they note something else that deepens the puzzle. The jet does not flicker aimlessly. Its position angle on the sky drifts only slightly over weeks, indicating that the source region on the object's surface is somehow locked into a stable orientation with respect to the Sun. In a natural comet, jets tend to sweep around as the nucleus spins, tracing spiral fans like the arcs of rotating sprinklers. Here, instead, a single, narrow beam appears to track the star with a steadiness that suggests a fixed relationship between the axis of rotation and the direction of the Sun. A full understanding of that geometry will require careful modeling of the spin state, but even before that work is complete, The January imagery signals a change of category. 3IATLAS can no longer be treated as a standard piece of icy debris wandering through the inner solar system. It has moved into a class of objects that do not simply respond to the environment, but appear to oppose it. And that shift in behavior forces every model of its nature and history back onto the drawing board. With the March encounter with Jupiter's realm drawing nearer each day, the presence of a stable sunward jet transforms the object from an odd comet into a live physics experiment, already underway and unfolding in real time across the solar system. The reaction within the community is measured but intense. Teams working with ground-based observatories begin to reprocess archival images of 3IATLAS, searching for earlier overlooked signs of the same behavior hidden at the edge of sensitivity. Analysts revisit photometric curves to see whether subtle brightness variations might already carry the imprint of a preferred direction of outgassing. Instrument specialists check calibration pipelines, looking for any path by which scattered light or detector quirks could mimic a narrow sunward beam, and one by one, those ordinary explanations fall away. The feature remains, embedded in the data like an instruction written into the trajectory of the object itself. Slowly, a new framing takes hold. Instead of asking how a normal comet could briefly act in such an abnormal way, astronomers begin to consider the possibility that 3IATLAS has never been a normal comet at all. The narrow jet, the resistance to solar forces, the persistent alignment with the sun, all point toward an underlying mechanism that is not yet understood. In place of a minor curiosity, the solar system now hosts a moving, active anomaly. And every new observation will have to reckon with the fact that the object seems to behave less like a passive fragment of ice and rock, and more like a system with internal structure and direction. The effort to understand 3IATLAS now turns toward the basic physics that should govern any icy body under the influence of the sun. In standard comet science, the behavior of outflowing material is well charted. A comet nucleus is a mixture of frozen gases and dust, a porous, fragile object that awakens when sunlight begins to warm its surface. As the ices near the skin of the nucleus heat, they sublimate, passing directly from solid to gas and escaping into surrounding space. This gas carries dust grains with it and builds a diffuse cloud called the coma. From this coma, forces from the sun shape the familiar tails. One force is solar radiation pressure. Light carries momentum, and each photon that strikes a dust particle gives it a tiny push. For large grains, this push is small, but for very fine particles, the acceleration can be significant. Over time, radiation pressure drives these light grains away from the sun, stretching them into long, graceful dust tails that curve gently under the combined effect of the comet's motion and the steady push of light. The second sculpting agent is the solar wind, a stream of charged particles flowing outward from the sun at hundreds of kilometers per second. When this wind encounters ionized gas in the comet's coma, it drags the ionized material with it, forming straight, bluish ion tails that point almost directly away from the star. These two influences are so consistent that comet tails have become a kind of compass in space, always leaning away from the solar source. In this framework, a sunward-pointing tail is inherently unstable. Any cloud of small particles released toward the sun should be quickly turned around, blown back and outward until it joins the general flow. Even structures that appear sunward in some images are usually explained as projection effects, where a tail that really points slightly away from the sun happens to lie close to the line of sight, and thus appears to extend inward. This behavior has been confirmed for many comets over decades of observation, from small, short-period objects that return frequently to long-period visitors that sweep in from the outer reservoirs of the solar system. The arrival of interstellar objects has only reinforced this picture. The first known visitor from beyond the solar system, a body cataloged as the First Eye object, shows unusual non-gravitational accelerations, but does not present a stable sunward jet of material. The second known interstellar comet behaves in many ways like an ordinary comet, with a more typical dust and gas tail structure. Against this background, the jet of 3IATLAS is not simply a curiosity, but a direct challenge to the foundation of comet tail physics. Its orientation remains stubbornly sunward over multiple observing epochs. The structure is narrow and sharply defined, with a length estimated at several 100,000 kilometers. At that scale, even modest lateral forces should cause significant spreading, yet the brightness profile remains consistent with a beam that preserves its coherence over a vast distance. This suggests that either the material in the jet is unusually massive, with particles so dense that radiation pressure and solar wind have little effect, or that some mechanism actively maintains the structure against environmental disturbances. Both possibilities are unsettling. If the jet consists of very large or very heavy grains, then the energy required to loft them to the observed distances would be enormous for a small nucleus. Sublimation-driven outgassing can accelerate fine dust and gas, but accelerating dense particles into a collimated stream over lunar-scale distances implies an energy budget more typical of constrained venting than of broad surface evaporation. On the other hand, if the material is more conventional but somehow shielded from solar forces, then a new type of interaction must be at work, something that allows the jet to act as though it is less exposed to the surrounding medium than expectations allow. The brightness of the jet adds another layer to the puzzle. Observations indicate that it is not a faint, ghostly extension at the edge of detectability, but a strong feature rivaling or exceeding the brightness of more conventional tail components. In normal comets, the smallest, most reflective dust grains are rapidly driven away by radiation pressure, leaving behind a mix that tends to be darker and more diffuse. Instead, the sunward jet of 3IATLAS appears persistently luminous, as though the supply of bright particles is being sustained at a high rate, or the emitting material is intrinsically radiant in some way not yet characterized. When teams examine the temporal behavior of the jet, they find that it does not correspond to short-lived outbursts, the sudden flares sometimes seen when a comet's crust fractures and exposes fresh ice. Those events usually result in rapidly expanding shells of material that fade as the new surface sublimates and then cools. By contrast, the sunward jet of 3IATLAS is already present in data from July of the year 2025 and remains visible into January of the year 2026. This persistence over many months points toward a quasi-steady-state process. Something on or within the object is feeding a continuous, directed outflow along a preferred direction. Rather than a brief exhalation, it behaves more like a long, sustained breath. Simple models of passive outgassing struggle with this picture. For a standard comet nucleus, surface activity tends to move with the seasons of the orbit, responding to changing solar illumination. Active regions shift as the nucleus turns, and even in cases where a single jet dominates, the resulting plume usually describes a fan or spiral pattern as the object spins. The beam from 3IATLAS, however, behaves as though anchored to a specific relationship between the body and the sun, maintaining a roughly constant direction even as the object approaches, passes, and recedes. That behavior nudges the discussion away from the familiar language of seasonal heating and toward questions of internal structure and control. Some researchers explored the possibility that the nucleus might possess a complex topology, with deep fractures or conduits that focus gas flow through a narrow opening. In this picture, the jet would be a natural nozzle created by the intersection of cracks and cavities, perhaps formed during the object's long prior evolution in interstellar space. Yet this explanation still requires the direction of the opening to remain closely aligned with the sun over months, despite the orbital motion of the object. For that to happen, the spin axis must be configured in a very specific way, and the jet must emerge near a point on the surface that remains continuously illuminated. This requirement begins to tie the physical structure of the jet to the geometry of the spin state, a link that will draw dynamical studies into the heart of the mystery. Other investigators consider whether electrostatic effects or magnetic interactions could be shaping the jet. Dust grains in space can become electrically charged under solar ultraviolet light, and charged particles in the solar wind interact with magnetic fields. However, the large-scale structure of the sunward jet, its length, and its apparent resilience suggest that simple charging processes are unlikely to generate the required degree of collimation. Any such interaction would need to act in a sustained and directed manner, not merely sort particles by size or charge. As each conventional avenue is explored and found inadequate, the language used in internal reports and quiet workshops shifts. Terms like constrained flow, anisotropic outgassing, and focused emission begin to appear more often. The jet is no longer treated as just another plume. It is described instead as a manifestation of a particular energy release pattern, one that looks increasingly like a continuous operation rather than an incidental byproduct of surface warming. The distinction may seem subtle, but it represents a crucial step in how 3IATLAS is framed. A passive body responds to its environment. A system with internal structure and feedback can maintain a state that resists external forces. The sunward jet, standing against the combined push of light and wind, suggests that 3IATLAS belongs, at least for now, in the latter category. With that shift in thinking comes a new set of questions. If the jet behaves like the output of a nozzle, what shapes the flow at its base? If the energy driving it is not simply surface heating, where does it originate inside the object, and how is it regulated over time? If the structure holds stable as the object nears a complex gravitational interaction with Jupiter, does the jet play a role in fine-tuning that encounter? The answers to these questions remain out of reach, but the pattern is clear. A single, narrow beam of material, pointing defiantly toward the sun, has forced a reclassification of an entire object. What began as a comet candidate has become a test of whether the current understanding of natural outgassing processes is complete, or whether a different category of activity, perhaps even a different category of object, is now passing through the solar system. As the sunward jet of 3IATLAS moves from curiosity to central feature, attention turns from the broad sweep of tails to the fine structure of the coma itself. The object is small and distant, and even the best images record only a blurred core surrounded by a faint haze. To extract more information, astronomers resort to specialized processing techniques developed over years of comet studies. Among these tools is the Larsenina rotational gradient filter, a method that takes an image of the comet, rotates a copy of it by a small angle around the nucleus, and subtracts one from the other. In doing so, the smooth, roughly symmetrical background of the coma cancels out, while any subtle directional features stand out in sharpened relief. Applied to 3IATLAS, this filter reveals a pattern that is both intricate and unexpectedly ordered. Instead of a single plume, the coma resolves into a complex system of 3 distinct jets. 2 of them are faint, angled away from the main axis, contributing to a delicate, fan-like structure when seen in the processed frames. The third is the already recognized sunward beam, but in the filtered images, it appears even more striking. It rises straight from the central condensation, like a narrow spine, far brighter than the secondary jets, and extending well beyond them, a dominant component rather than a minor addition. The contrast enhancement makes clear that this feature does not broaden with distance in the way that dust fans usually do. Other jets in other comets tend to flare outward, their edges softening as gas and dust disperse into the surrounding vacuum. The principal jet of 3IATLAS, even under aggressive processing, retains a tight profile, its brightness declining gradually along its length, but its width changing only slightly from base to tip. This behavior supports the view that the outflow is not only strong, but also highly directional, as though guided by a channel that constrains its initial spread. When sequences of such filtered images are assembled over weeks, another important pattern emerges. The secondary jets show signs of modulation. Their apparent angles and intensities vary with time in a way that suggests the spin of the nucleus. As the object rotates, regions of surface activity move in and out of direct sunlight, switching on and off, or changing intensity in a periodic way. In the processed images, this rotation manifests as subtle shifts and rhythmic brightening and dimming of the fainter jets. They behave much like familiar cometary plumes tied to discrete patches on a spinning, irregular nucleus. The main sunward spike behaves differently. Its core brightness fluctuates, but its orientation with respect to the sun changes only slightly. The jet seems to process slowly, describing a small cone around an average direction that remains close to the sunline. This suggests that the source region feeding the jet lies near a special point on the surface, close to the subsolar point where the sun is almost overhead at all times given the object's spin. In such a configuration, a source near the pole of rotation on a nearly sun-pointing axis would remain illuminated through most of the orbit, while lower latitude regions pass through day and night cycles. The filtered images hint at precisely this division. The 2 weaker jets appear compatible with more ordinary active patches at lower latitudes, while the central beam aligns with a near-polar, persistently heated region. That geometry already begins to link the internal structure of the nucleus to its spin axis and to the external reference of the sun. Coma modeling specialists take these processed images and attempt to reproduce them with synthetic simulations. In these models, a virtual nucleus rotates in space, while small parcels of gas and dust are released from specific surface areas, then are pushed around by idealized radiation pressure and solar wind. By adjusting parameters such as jet opening angle, particle size distribution, and emission speed, the models can recreate a broad range of cometary appearances. For 3IATLAS, matching the pair of faint secondary jets is not especially difficult. With reasonable assumptions about emission cones and rotation rates, simulated frames can produce similar angled plumes that fan out and blend into the diffuse coma. The challenge is to match the main sunward jet. In model after model, any attempt to launch material directly toward the sun leads to rapid bending and dispersal. Even with large, heavy particles, the simulated jets either curve away from the star under the influence of radiation pressure, or, if they are given very high initial speeds, they disperse into broad streaks instead of remaining collimated. To maintain a narrow beam over hundreds of thousands of kilometers, the simulations must be pushed into regimes that strain credulity. The required emission velocities become so high that the gas and dust behave more like the exhaust from a high-energy venting event than like the soft flow of sublimating ice. Alternatively, the opening angle of the jet must be set to be extremely small, essentially a beam rather than a cone, and the particle sizes must be chosen to be so large and dense that they begin to resemble gravel rather than dust. Even then, the resulting structures are fragile, easily disrupted by small perturbations. Yet the real jet, as recorded in the sky data, shows no such fragility. It persists through changes in the viewing geometry, through gradual variation in the distance to the sun, and through the subtle influence of the object's rotation, always reasserting its basic shape. The Larsenina filter also reveals hints of fainter structures trailing along the path of the object, sometimes described as a phantom trail. This elongated feature does not share the striking brightness of the main jet, but its presence suggests that material is being left along the orbit, perhaps from previous episodes of activity. Its relation to the triple jet system is not yet clear, but its existence adds another layer to the overall picture of an object that seems to manage multiple, distinct outflow channels over time. Spectroscopic observations, where astronomers spread the light from the coma into its constituent colors, add further nuance. They indicate that the overall composition of the gas is broadly compatible with that of other comets, with familiar molecules and atomic fragments appearing in the data. However, the detailed distribution of emissions along the sunward jet versus the other parts of the coma appears uneven. There are indications that the jet carries a different mix of particle sizes, or perhaps a different balance of volatiles to dust than the surrounding haze. Some teams interpret this as evidence that the source region of the jet taps a reservoir deeper within the nucleus, one that has been shielded from interstellar radiation for long periods and thus retains a more pristine composition. Others suggest that the outflow process itself may be sorting material, perhaps accelerating certain grain sizes preferentially. In either case, the combination of compositional hints and structural stability reinforces the view that the main jet represents a distinct mode of activity, not just a stronger version of the same simple sublimation that powers the weaker plumes. Over months, the accumulating image sets serve as a record of the object's behavior under changing solar conditions. Early frames, when 3IATLAS is farther from the Sun, already show the jet in place, although shorter and somewhat fainter. Later frames, as the object draws nearer to the inner solar system, reveal a gradual increase in brightness and length, but not a qualitative change in structure. There is no sudden flare in which a previously quiescent body erupts. Rather, there is a steady scaling up of an already established pattern. This continuity over time complicates ideas that rely on transient fractures or one-off internal releases. Instead, the picture that emerges is one of a system that has been in a particular operational mode for an extended period, maintaining its relationship to the Sun and its characteristic outflow geometry across a significant portion of its inbound journey. In private workshops and analytical notes, some researchers begin to describe the jet in terms usually reserved for engineered flows. Words like collimation, nozzle, and thrust vectoring appear alongside more traditional cometary terminology. Care is taken not to leap to conclusions about artificiality, but the language reflects a genuine difficulty in reconciling the observed stability and directionality with known natural processes. The jet looks, in many of its aspects, like the controlled output of a system that has internal constraints in feedback, rather than the incidental spray of a melting surface. The filtered images, stripped of smooth background and enhanced to reveal only the underlying structure, show a simple but disturbing arrangement. A central, bright jet pointing almost exactly sunward, flanked by two subordinate plumes, embedded in a faint, possibly trailing skeleton along the orbit. It is an arrangement that seems to encode a hierarchy of processes, with one dominant, persistent channel and several lesser, more conventional ones. At this stage, the anomaly is no longer confined to a single puzzling data point. It is present in the morphology of the coma, in the time evolution of the features, in the inferred energy budgets, and in the emerging link between the jet and the object's rotation. The next step is to quantify that rotation and its alignment with the wider architecture of the solar system. To understand why the central jet insists on pointing toward the Sun, investigators must map the spin axis of 3IATLAS and its trajectory through space. That effort will shift the focus from the microscopic physics of grains and gas to the macroscopic geometry of orbits and poles. And it will reveal that the anomaly in the coma is matched by an equally unsettling anomaly in the way the object moves and turns. To understand why the main jet of 3IATLAS insists on pointing toward the sun, investigators are forced to leave the immediate surroundings of the nucleus and examine how the entire body spins through space. The key lies in the tiny, patient motions of the jet itself. Although the sunward beam appears almost fixed in direction, precise measurements of its position angle over many weeks reveal a slow, rhythmic wobble superimposed on that apparent stability. Night after night, images taken from space-based observatories and large ground-based telescopes are aligned and compared. The axis of the jet is measured relative to background stars and to the projected direction of the sun. Small deviations are recorded, fractions of a degree at a time, plotted against the changing geometry of the orbit and the line of sight. When these measurements are assembled into a continuous curve, they begin to trace the story of a spinning body whose pole is not random at all. In standard celestial mechanics, the spin axis of a small object, like a comet, is oriented in an arbitrary direction, a leftover from its formation and from past collisions and torques. Over long timescales, slow processes such as outgassing or distant gravitational nudges can modify that orientation. But for the most part, there is no reason to expect a particular alignment with any external reference. A typical comet spins like a tossed stone, its axis pointed somewhere on the sky, changing only gradually, if at all. In this context, the expectation for an interstellar visitor is even more chaotic. Such an object has wandered through the gravitational fields and radiation environments of other stars, passing through complex histories long before it approaches the sun. Its rotation should bear the imprint of those distant interactions and carry no special preference for the geometry of the solar system. The data for 3IATLAS tell a different story. By modeling the observed wobble of the sunward jet under the assumption that the jet emerges from a near-polar region on the nucleus, dynamical specialists reconstruct the orientation of the rotation axis in three-dimensional space. They treat the object as a spinning top and use the way the jet sweeps a small cone in the sky over time to deduce where the pole points. After fitting the variations and adjusting for the changing vantage point as the object moves along its orbit, the solution that best matches the data places the spin axis in a startling configuration. Within measurement uncertainties, the pole of 3IATLAS points almost directly at the sun, deviating by only a handful of degrees from the line connecting the nucleus to the star. In practical terms, this means that as the object travels through the inner solar system, one hemisphere faces continuous day, while the opposite hemisphere remains in near permanent night, a configuration resembling an eternal solstice, locked into place. In such a state, any active region near the sunward pole would be illuminated almost constantly, feeding a steady outflow that naturally aligns with the sunline. This geometry immediately explains why the main jet maintains its orientation so well, but it also poses a deeper question. Why is the pole aligned in this way at all? Statistical arguments provide an initial sense of how unusual this is. If spin axes of interstellar objects are distributed randomly across the sky, the likelihood that any one of them happens to lie within, for example, about 7 degrees of the sun direction at the time of observation, is quite small. The sky covers a sphere of directions, and a cone of 7 degrees around a given point occupies only a tiny fraction of that total area. The precise number depends on how the alignment is defined, but even conservative estimates place the probability at roughly 1 chance in many thousands for a random pole to fall so close to the solar line by accident. In principle, gravitational torques from the sun could slowly reorient a spinning body over long periods, but 3IATLAS has not been near the star long enough for such gentle forces to have a major effect. Its passage through the inner solar system occurs over only a short span of time, and the tidal influences at the distances involved are weak. There is simply not enough opportunity for the sun to twist the spin axis into its current position. The most straightforward interpretation is that the object arrived already aligned, carrying this configuration from its journey through interstellar space. That conclusion introduces a layer of discomfort. A 1 in many thousands chance event can happen, but when such a low probability pattern coincides with other anomalies, the assumption of pure randomness grows fragile. In the case of 3IATLAS, the polar alignment does not stand alone. It sits alongside the existence of a stable sunward jet that defies standard outgassing behavior And it precedes a trajectory that will bring the object into a near grazing encounter with the outer limits of Jupiter's gravitational domain. Each of these features can be examined separately, but there is an unavoidable tendency to ask whether they share a common cause. Before combining them, however, the spin state itself must be explored in more detail. Light curve analysis offers another route to the same conclusion. As 3I-ATLAS rotates, its overall brightness fluctuates slightly, depending on which facets of the nucleus and which active regions face the observer and the sun. By continuously monitoring the object and measuring these variations, astronomers derive a rotation period and constraints on the shape. The light curves of 3I-ATLAS suggest an elongated body rather than a perfect sphere, with one end likely more heavily sculpted by activity than the other. In most comets, such asymmetry leads to rotational evolution. The outgassing itself acts like a network of small thrusters, pushing on the irregular mass distribution and gradually altering the spin rate and axis orientation, in a process often referred to as a thermal torque effect. Comets can speed up, slow down, or even tumble into complex rotational states as their jets push unevenly over time. In the case of 3I-ATLAS, the persistent, powerful sunward jet should, by intuition, be an especially strong source of such torques. Yet, the reconstructed spin axis appears stable over the observed interval. The jet remains locked to the sunline within a narrow cone, and the rotation period shows no large, obvious drifts that would indicate rapid evolution. This combination suggests that the jet's action is either very symmetrically arranged around the mass distribution in a way that cancels net torques, or that some internal mechanism is actively damping changes in orientation. Both possibilities stretch the usual picture of a fragile, loosely held rebel pile responding passively to forces at its surface. In orbital simulations, researchers explore what would happen if a similar interstellar body with a randomly oriented spin axis were subjected to the same pattern of outgassing. The result in most runs is a gradual wandering of the pole across the sky, not a steady stare at the sun. To achieve a locked configuration where a single hemisphere remains illuminated, the initial spin state must already meet very specific conditions. Once such a configuration is in place, it can be stable, but the path to arriving there by chance seems narrow. Some teams propose that perhaps 3I-ATLAS passed close to another massive body long before entering the solar system, and that encounter torqued it into its current state. Others note that long-term exposure to asymmetric mass loss in its original system could in principle have guided the axis over time. These ideas keep the discussion within the realm of natural processes, but at the cost of layering one low-probability event atop another. Outside the purely dynamical arguments, the physical consequences of the alignment are immediate. A polar region in constant sunlight receives sustained heating, potentially boring deep into the interior. If the composition of the nucleus includes layers or pockets of volatile rich material, a polar solstice configuration could tunnel into that reservoir and maintain high activity for extended periods. This offers a natural reason for the main jet to be so persistent and powerful. However, it also raises the issue of how the nucleus remains intact. Continuous venting from a single polar area, especially in the presence of a bright, narrow jet, might be expected to erode a deep pit or even destabilize the structure. Yet, there is no obvious signature of major fragmentation so far. Instead, the object maintains its coherence while offering a carefully directed outflow along its pole. When this directed outflow is combined in models with the pole alignment, the behavior of the main jet begins to resemble a thruster mounted along the spin axis of a spacecraft, firing more or less continuously along a specific line in space. The analogy is conceptual rather than literal, but it is difficult to avoid. A polar thruster can adjust speed along the direction of motion, or refine a trajectory with minimal impact on the orientation of the body, particularly if it acts in short, controlled burns. In the case of 3I-ATLAS, the jet appears persistent rather than pulsed, yet its association with a pole that points at the sun and with an orbit that lies almost in the planetary plane invites comparisons to guided motion. At this stage, most investigators remain cautious. The language in formal reports emphasizes that a small, non-zero fraction of random interstellar objects will, by sheer chance, exhibit unusual alignments. The fact that 3I-ATLAS presents one such configuration does not, by itself, mandate an exotic explanation. However, the alignment is not being evaluated in isolation. It is one component of a growing pattern, and as the models become more refined, the fit between a simple random origin and the observed geometry becomes increasingly strained. The spin axis points toward the sun within a narrow angle. The main jet erupts from near that axis, providing a continuous sunward thrust-like flow. The object's path through the solar system, as other studies are beginning to show, lies close to the ecliptic, the plane in which the major planets travel. Each of these elements is surprising on its own. Together, they begin to form the outline of a configuration that looks less like a tossed stone, and more like a system whose orientation and motion are coupled. The next natural step is to examine that path in detail, to set the spin alignment against the backdrop of the solar system's flattened architecture, and to ask how likely it is that an interstellar visitor would slide so neatly along the traffic lane of the planets while keeping its polar jet aimed at the star that dominates that plane. With the spin axis of 3IATLAS now inferred to be pointing close to the Sun, orbital dynamicists turn their attention to the path the object follows through the solar system. Every small body that enters the Sun's gravitational field traces a trajectory that can be described by a set of orbital elements, and these elements reveal how that path is oriented relative to the broader architecture of planetary orbits. The major planets circle the Sun in a flattened disk called the ecliptic plane, a relic of the rotating cloud from which the system formed. Most comets and asteroids that belong to the solar system itself also move close to this plane, although many long-period comets arrive on orbits that are tilted at substantial angles. Interstellar visitors, however, are expected to show no preference at all. They come from random directions, shaped by the gravity of their home systems and the perturbations of their journeys through the galaxy. There is no reason for them to respect the thin sheet of the ecliptic. This expectation finds support in the first two interstellar objects detected. The first, a slender, tumbling body that passed through the inner solar system in the year 2017, arrived on a steeply inclined orbit, cutting across the planetary plane and departing into the northern sky. The second, a more conventional-looking interstellar comet discovered in the year 2019, also followed a path that was distinctly tilted, entering from an angle that showed no special alignment with the orbits of the planets. Against this background, the trajectory of 3IATLAS stands out. When its incoming path is reconstructed from the accumulating astrometric measurements, the orbit proves to be almost coplanar with the ecliptic. The inclination, the angle between its orbital plane and that of Earth, is small. In simple terms, 3IATLAS is not diving in from above or below the planetary disk. It is sliding along it, sharing the same broad plane as Earth, Jupiter, and the other major worlds. This alignment in itself is already uncommon. Since interstellar arrivals are expected to be oriented randomly in 3 dimensions, only a small fraction will happen to match the special orientation of the ecliptic within a narrow tolerance. When this orbital alignment is combined with the spin axis orientation, the improbability multiplies. The pole of 3IATLAS points toward the Sun within a few degrees, and its orbit lies close to the plane that passes through the Sun and the planetary orbits. In geometric terms, the object's spin axis is nearly orthogonal to the orbital plane, and that axis coincides with the direction of the central star. This arrangement ensures that as 3IATLAS travels along its low inclination path, one pole remains in persistent daylight, while the main jet, anchored near that pole, can remain aimed at the Sun and roughly along the line of motion. Statisticians in the field approach this configuration with the tools of probability theory. If spin axes are assumed to be distributed uniformly over the sphere of possible directions and orbital inclinations are likewise unconstrained for interstellar arrivals, the chance of a single object having both a low inclination orbit and a spin axis aligned with the Sun within a few degrees becomes small. Different teams use slightly different thresholds and methods, but results cluster around odds in the vicinity of 1 part in several thousands to 1 part in 10,000. These figures are not exact, but they convey the central point. The geometry of 3IATLAS is exceptional in a way that is unlikely to be explained by pure chance if the underlying distributions are truly random. One can always invoke the argument that rare events do occur, and in a galaxy with vast numbers of comet-like bodies, even low probability configurations will occasionally appear. However, in the specific context of human observation, the third known interstellar object presenting such a configuration so soon after the first two, which did not, is difficult to ignore. The orbital alignment also has practical consequences for the likelihood of planetary encounters. An object slicing through the solar system at a steep angle spends little time near the regions where planets travel, and close approaches are relatively rare. An object moving almost in the ecliptic, by contrast, shares the same general track as the planets, and thus has a much higher chance of passing close to one of them if the timing and radial distance align. This is precisely the case with 3IATLAS. Its path, projected forward, brings it outward past the orbit of Mars and toward the realm of the gas giants. There, its low inclination trajectory intersects the extended gravitational domain of Jupiter, the most massive planet. Simulations show that the object will pass near the outer boundary of Jupiter's sphere of influence, a region defined not by solid surfaces, but by the point at which Jupiter's gravity begins to compete seriously with that of the Sun. In orbital mechanics, this region is characterized by a parameter often referred to as the Hill radius, beyond which the Sun dominates, and within which stable satellites of Jupiter can exist. 3IATLAS will not plunge deep into this sphere, but it will graze its outer fringe, passing at a distance of tens of millions of kilometers from the planet itself. When this upcoming encounter is overlaid on the geometric picture already developed, the sense of a carefully tuned arrangement deepens. A spinning body with its pole pointing at the Sun, carrying a powerful sunward jet from its polar region, is moving along nearly the same plane as the planets and will soon pass close to the edge of the gravitational zone where Jupiter's control begins. The orientation of the jet, the positioning of the pole, and the flatness of the trajectory combine to create a situation in which any material released in the vicinity of the encounter could, under the right conditions, interact strongly with Jupiter's gravity. The geometry effectively sets up a potential handoff point between the interstellar object and the Jovian system. That does not yet mean that such a handoff will occur, but it creates the opportunity in a way that a randomly inclined path would not. Dynamicists run large ensembles of orbital simulations, injecting hypothetical debris fragments into the system during the planned passage and tracking their fates under the combined gravitational pull of Jupiter and the Sun. These models explore a wide range of ejection times, directions, and speeds. For most random configurations, fragments released at interstellar transit speeds simply continue outward, their high relative velocity preventing capture. However, the simulations reveal that if a fragment could shed a very large portion of its speed relative to Jupiter at just the right point near the Hill radius, it could drop into a bound orbit around the planet. The required change in velocity is large, but the geometry of 3IATLAS makes the timing problem easier than it would otherwise be. Because the object is moving within the planetary plane, and because its approach and departure directions are well defined in that frame, there are specific windows during the encounter in which a fragment, if separated with the right impulse, would have a reasonable chance of becoming a new Jovian satellite. This scenario is theoretical, and the energy demands are severe, but it marks a transition in how the encounter is conceptualized. Instead of viewing 3IATLAS as a transient visitor passing through empty space, analysts begin to see its path as threading a narrow corridor through a complex gravitational landscape. The low inclination orbit ensures that the object spends more time close to Jupiter's orbital distance than an inclined object would. The polar alignment ensures that any persistent, jet-driven operations can remain oriented along a stable reference direction throughout this phase. The combined configuration resembles a set of initial conditions that are unusually well suited for a targeted interaction with the Jovian system, whether that interaction is a simple gravitational flyby or something more elaborate involving the release of material. This way of framing the situation is not yet mainstream, and many researchers emphasize that interstellar objects must, by their nature, exhibit a wide variety of orbits and spin states, some of which will inevitably be rare. Still, as more details of 3IATLAS emerge, the list of unusual properties grows. The sunward jet that resists solar forces, the spin axis locked to the sunline, the nearly ecliptic orbital plane, and now the impending passage near Jupiter's Hill radius all point in the same general direction, away from the simple picture of a random passive body, and toward a system whose motion and orientation appear coupled. In closed sessions and in speculative sections of drafts, some investigators allow themselves to ask a more pointed question. If a hypothetical engineered probe or vehicle were designed to use a star for navigation and to interact with a giant planet for a gravity assist or for deployment of secondary units, what path would it follow? The answer, at least in broad outline, would likely involve a low inclination trajectory along the planetary plane, a stable alignment of a main thrust vector with the star, and a carefully chosen passage near the boundary where the giant's gravitational reach begins. 3IATLAS, as reconstructed from the data, seems to approximate this arrangement. The comparison is not proof, but it is striking enough that it begins to guide observational priorities. With a critical encounter looming in March of the year 2026, attention starts to shift from explaining how 3IATLAS arrived in its current configuration to preparing for what might happen as it crosses Jupiter's invisible boundary. That preparation will require a clear understanding of the energy involved in any potential capture and a sober assessment of whether known natural processes can supply it. The orbital geometry sets the stage, But the capture problem defines the difficulty, and it is to that problem that the next line of investigation turns. As the orbit of 3IATLAS carries it away from the inner solar system and outward toward the domain of the giant planets, the nature of the mystery begins to shift. Near the Sun, the dominant questions concern jets, spin axes, and the resistance of a narrow beam to radiation and wind. Farther out, where Jupiter's gravity starts to compete with the Sun's control, a new set of questions arises, centered on what might happen when an interstellar object passes close to the boundary of a massive planet's influence. That boundary is not a physical surface. It is a region defined by gravitational balance, where the pull of Jupiter on a nearby body becomes strong enough that, under the right conditions, the smaller object can be captured into orbit. Orbital dynamicists describe this region using a quantity known as the Hill radius, a characteristic distance from the planet within which its gravity dominates over the tidal pull of the Sun for the purpose of holding satellites. For Jupiter, this radius is enormous, stretching far beyond its visible cloud tops and well into the surrounding space. 3IATLAS is on course to skim the outer parts of this region, passing at a distance of tens of millions of kilometers from the planet, far beyond any of the known Galilean moons, but still within the weak outer layers of Jupiter's gravitational reach. In the months leading up to the encounter, simulations of the path of 3IATLAS become increasingly detailed. Using the current best-fit orbital elements, teams propagate the motion forward through time, including the gravitational forces from the Sun, Jupiter, and the other major planets. They also fold in the measured non-gravitational accelerations associated with the sunward jet, treating it as a continuous, gentle thrust along the line to the Sun. These models show that the object will reach its closest approach to Jupiter's region in mid-March of the year 2026, moving at a relative speed of roughly tens of kilometers per second. At that speed, 3IATLAS is a fast visitor, skimming the edge of Jupiter's Hill sphere too quickly to be captured as a whole. The gravitational pull of the planet will deflect its path slightly, bending its trajectory, but not enough to bind it. The interstellar object will continue on, altered but not stopped, heading back toward the darkness of interstellar space. Under normal circumstances, that would be the end of the story. A high-speed flyby through the outer Jovian environment would be a transient event, leaving no lasting trace beyond a subtle change in the object's incoming and outgoing directions. However, the combination of the unusual jet, the polar alignment, and the low-inclination orbit prompts analysts to consider more complex possibilities. They ask what would happen if 3IATLAS were not a simple, single body, but a system capable of shedding fragments or secondary objects in a controlled way during the encounter. The key concept in this context is capture. For any part of 3IATLAS to remain in the Jovian system as a new satellite, that part must lose almost all of its relative speed with respect to Jupiter. In simple terms, the fragment must slow down from an incoming speed of several tens of kilometers per second to a speed of only a few kilometers per second or less, the scale of velocities characteristic of bound orbits at the distance of the encounter. The difference between these speeds represents an enormous change in kinetic energy. Natural fragmentation events, such as a comet splitting under thermal stress or rotational breakup, can impart small kicks to pieces, perhaps tens of meters per second, or, in extreme cases, up to a kilometer per second. These values are tiny compared to the tens of kilometers per second needed to turn a fast flyby into a bound orbit. In gravitational capture problems, the energy required to change an object from a visitor to a permanent resident is usually provided by complex interactions involving multiple bodies, such as a fragment passing close to a moon and exchanging momentum, or by mechanisms such as gas drag within a dense disk. In the sparse outer regions of Jupiter's Hill sphere at the present epoch, none of these natural energy exchange pathways are strong. There is no substantial gas disk, and the known moons lie well inside the projected track of 3IATLAS. The likelihood of a fragment happening to pass close enough to a moon for a three-body gravitational capture is extremely small, especially given the speed and distant trajectory of the interstellar object. These considerations lead to a simple conclusion. Under ordinary conditions, and in the absence of large energy losses, 3IATLAS will not leave anything behind. Any small pieces produced by natural processes would share nearly the same high speed as the parent body and would merely follow it out of the system. For a fragment to become bound to Jupiter, some mechanism must provide a very large, directed change in velocity. This is where the presence of the long-lived sunward jet enters the discussion in a new way. Near the Sun, the jet has been treated primarily as a diagnostic of internal processes and as a source of non-gravitational accelerations that slightly alter the path of the object. Farther from the Sun, near Jupiter's realm, the same jet can be considered as a potential tool. If the jet truly represents a persistent directional outflow, then, in principle, it can act as a form of thrust, applying a continuous small push over long timescales. The net effect of such thrust, accumulated over months, can be significant, especially if it is aligned with the motion in a way that either increases or decreases the speed along the track. In the data, the jet of 3IATLAS is oriented almost exactly along the line toward the Sun. And because the object's path through the inner solar system lies close to the ecliptic plane, there are periods during which this jet is nearly aligned with its direction of motion relative to Jupiter as well. In conceptual diagrams drawn on whiteboards and in internal reports, dynamicists sketch an elongated path that approaches Jupiter's orbital radius, crosses the outer part of the Hill sphere, and then recedes. They mark a region along this path where the relative geometry of the Sun, Jupiter, and 3IATLAS makes it possible for a directed outflow along the sunline to modify the speed of a potential fragment with respect to Jupiter. In these sketches, the interstellar object functions like a carrier passing through a drop zone. If a smaller body were to be separated from it at the right moment, and if that separation were accompanied by a strong, directed impulse opposite to the incoming motion, the fragment could slow enough to fall into a bound orbit around Jupiter. The energy required for such an impulse remains daunting. To shed tens of kilometers per second of relative speed in a brief interval demands a concentrated release of energy far greater than what is typically seen in natural cometary outbursts. Calculations show that the energy per unit mass involved would approach levels associated with powerful explosive devices if confined to small, focused fragments. This is why, in standard models, such captures are dismissed as essentially impossible for simple frozen bodies. Yet 3IATLAS is not behaving like a simple frozen body, at least in the inner solar system. Its sunward jet has already demonstrated that it can sustain a directed outflow against solar forces over enormous distances. Its polar alignment has shown that this outflow is anchored to a stable orientation. Its low inclination orbit has placed it in a configuration where interactions with Jupiter's gravity are enhanced. As these facts accumulate, the idea that the object might be capable of more than passive venting, possibly including controlled, high-energy events, can no longer be dismissed without consideration. Speculative frameworks begin to appear, carefully marked as such. Some researchers invoke the concept of an autonomous interstellar probe, designed to use natural gravitational fields for navigation and deployment. In this framework, a main vehicle could perform a fast flyby of a planetary system, adjusting its trajectory with long-duration, low-thrust operations, akin to the persistent jet, while also having the capacity to release smaller units with short, high-impulse events when conditions are right. The outer regions of Jupiter's Hill sphere in this view would be a suitable place to deploy long-term monitoring devices. A fragment, given the right change in velocity, could settle into a distant orbit, using Jupiter as an anchor to remain in the system for millions of years, silently observing. These ideas remain firmly in the realm of hypothesis, but they influence how the upcoming encounter is framed. The key point is that March of the year 2026 offers a testable distinction between two broad categories of explanation. If 3IATLAS passes through Jupiter's Hill sphere and leaves nothing behind, then all the unusual geometry in jet behavior, however puzzling, can still be folded into an expanded understanding of natural cometary and interstellar processes. The object would remain anomalous, but ultimately transient, a case study in extreme but possibly natural behavior. If, however, careful monitoring reveals that something does remain, that a new, faint satellite appears in the outer Jovian system where none existed before, then the energy gap between natural fragmentation and the required capture becomes very difficult to bridge without invoking controlled maneuvers. In preparation for this test, observatories on Earth and spacecraft in the Jovian system adjust their plans. Survey telescopes map the background star fields near Jupiter's track so that any new moving point sources can be detected after the encounter. Radio instruments prepare to listen for subtle disturbances in the plasma environment that might indicate energetic events. The Juno spacecraft, already in orbit around Jupiter, adapts its observing schedule to be as ready as its path allows to sense any changes in the magnetosphere or any unexpected luminous phenomena in the weeks around the passage. In effect, the outer reaches of Jupiter's gravitational domain become the stage for an experiment that no one planned but that the solar system now offers. An interstellar object with a sunward jet, a polar alignment, and a low inclination orbit will thread the edge of that domain at high speed. The question that hangs over the modeling efforts is simple and stark. When it leaves, will the Jovian system be unchanged? Or will there be a new, faint companion circling the giant planet? A small, silent moon whose existence cannot be easily explained as an accident. As the date of the encounter with Jupiter's realm draws nearer, the focus of the analysis narrows to a single, unforgiving question about energy. The geometry of 3I-ATLAS and its path through the outer reaches of the Jovian hill sphere has been established. The conditions under which a fragment could, in principle, be captured into orbit around Jupiter have been mapped. What remains is to confront the scale of the velocity change required to make that capture real, and to compare it with everything that is known about natural fragmentation events in small icy bodies. The result of that comparison is stark. At the time of closest approach to Jupiter's gravitational domain, 3I-ATLAS is expected to be moving at a relative speed on the order of 66 kilometers per second. Jupiter's own escape speed, the threshold below which a small object can remain bound to the planet rather than flying away, depends on distance. Near the cloud tops, it is high, roughly 60 kilometers per second, befitting a massive world. Far out, near the distance at which 3I-ATLAS will cross the outer layers of the hill sphere, the effective escape speed is far lower, only a few kilometers per second. Calculations show that at the projected approach distance, an object must be moving no faster than about 2 or so kilometers per second relative to Jupiter if it is to have any hope of being captured into a stable orbit. 3I-ATLAS, however, is rushing past at more than 60 kilometers per second. To turn any part of it into a new Jovian moon, that part must somehow shed roughly 64 kilometers per second of speed. This is not a small correction. It is a near total cancellation of motion relative to the planet, analogous to a stone thrown at tremendous speed that must be halted almost completely in mid-flight. In kinetic terms, the energy associated with a given mass increases with the square of its speed. Doubling the speed quadruples the energy. Reducing the speed of a fragment from tens of kilometers per second down to a few kilometers per second demands an enormous removal of energy. If this change is to occur over a short time during the hill sphere passage, the power involved is extreme. Natural fragmentation events in comets are dramatic on human scales, but modest on celestial ones. When a comet nucleus splits due to internal pressure, thermal stress, or rotational instability, pieces can be flung away, but the separation speeds are typically measured in meters per second. In the most violent cases, where pockets of volatile material explode as they are heated, fragments might be accelerated to hundreds of meters per second, or, in exceptional circumstances, perhaps to a kilometer per second. These speeds represent energetic events by the standards of fragile, icy bodies, and they can significantly alter the appearance of a comet's coma and tails. Yet, they are tiny compared to the tens of kilometers per second required for Jovian capture in the case of 3I-ATLAS. To see the scale of the discrepancy more clearly, dynamicists construct simple comparisons. A fragment that needs to lose 60 kilometers per second of relative speed has about 30 times the speed of a fragment that is given a 2 kilometer per second kick in a violent natural outburst. Because the energy scales with speed squared, the energy difference between these two cases is on the order of a factor of 1,000. In other words, to slow a fragment of a given mass by 60 kilometers per second requires roughly 1,000 times more energy than to accelerate it by 2 kilometers per second. There is no known natural process inside small, icy bodies that can release such focused energy without destroying the material in the process. If volatile gases trapped beneath the surface were to build pressure until a catastrophic rupture, the resulting explosion might fragment the body into dust and vapor, but the fragments would not emerge as intact, compact objects with carefully tuned velocities. They would be shredded into clouds. Gravitational interactions can also alter velocities, but here again, the environment works against easy capture. To trade enough energy with Jupiter through gravitational slingshot effects, a fragment must pass very close to the planet or to one of its moons. 3I-ATLAS will not do this. Its path stays far from the heavy satellites in the dense inner gravitational field. The route through the outer hill sphere is too remote and too fast for multibody gravitational capture to play a major role. Without an external agent or an extended medium to provide drag, the only way to produce the required deceleration is through internal forces, and those, as far as natural comet physics goes, fall far short. The conclusion that follows is uncomfortable. If the Jovian system gains a new moon after the passage of 3I-ATLAS, and if that moon can be traced kinematically to material that once formed part of the interstellar object, then the change in energy required for capture is so great that it implicates a process beyond known natural fragmentation. In that scenario, some mechanism would have had to act like a braking thruster, delivering a large, directed impulse to the fragment in the brief window of the Hill sphere crossing. The word thruster in this context is not used lightly. A thruster is a device that expels mass in one direction to produce a force in the opposite direction, slowing or speeding a vehicle in space. The sunward jet of 3IATLAS, viewed near the Sun, already behaves like a continuous, low-level thruster aligned with the solar direction. It is a long-lived, focused outflow that exerts a small but persistent reaction force on the nucleus. Near Jupiter, if the same system were capable of briefly increasing its intensity or redirecting its output to act against the motion relative to the planet, it could, in principle, generate the necessary change in speed for a secondary body. The energy source for such a maneuver would need to be substantial. It could not be the slow, passive release of heat from solar illumination alone. Instead, it would require stored energy in some internal reservoir, released in a controlled way. In natural settings, such concentrated directional releases are not observed in comets. The jets of famous active comets are vigorous, but they do not provide the selective, near-total cancellation of orbital energy needed to perform a capture onto a giant planet from an interstellar trajectory. This is the crux of what analysts begin to call the energy budget paradox. On the one hand, a purely natural interpretation of 3IATLAS as an interstellar comet must accept that its passage by Jupiter will be a fleeting one, leaving no permanent mark. The energy requirements make any natural capture event effectively impossible. On the other hand, if observations in the months after the encounter reveal a new, faint object looping around Jupiter on a stable path that can be traced back to the March transit, then the energy accounting will not add up under a natural framework. The only way to reconcile such a finding with the laws of motion would be to posit a non-natural mechanism capable of producing the required braking impulse. In parallel with these theoretical arguments, observational plans refine the range of outcomes that would be considered decisive. A simple gravitational influence, such as a tiny deflection of 3IATLAS's path, would not be enough to settle the question, because such deflections are expected. What matters is whether a separate body appears where none existed, a fragment that is gravitationally bound to Jupiter, and whose orbital parameters match those predicted for a captured piece of the interstellar object. That match would be signaled by an orbit whose plane and orientation relate to the trajectory of 3IATLAS in a way consistent with a release during the Hill sphere crossing. Detecting such a body will not be trivial. The outer reaches of Jupiter's satellite system are sparsely populated by faint, distant moons, some of which remain poorly characterized. Adding a small new member to that population may only be possible through careful comparison of pre-encounter and post-encounter surveys, searching for point sources that have appeared where there were none, or for objects whose orbits do not fit the pattern of long-established Jovian satellites. Ground-based telescopes with wide fields of view and sensitive detectors will play a crucial role, as will any assets in space capable of imaging the region with high stability. The Juno spacecraft, though it orbits closer in, can contribute by monitoring for any unexpected changes in the magnetosphere or energetic particle environment that might accompany a powerful deceleration event, if such a thing occurs. Even a brief, intense burst of directed outflow from 3IATLAS could leave a detectable imprint in the plasma near Jupiter, a transient disturbance in the otherwise steady flow. In framing all of these possibilities, scientists increasingly lean on the concept of a technological signature, a term used to describe observational evidence that implies the action of technology without identifying its exact nature. A new moon in the Jovian system, appearing in temporal and dynamical coincidence with the passage of an interstellar object whose behavior already defies cometary norms, would be such a signature. It would not provide a photograph of machines or structures, but it would reveal an outcome that natural processes cannot plausibly achieve under the conditions at hand. The energy budget paradox, then, becomes a filter. It separates the outcomes of the March encounter into two broad classes. In one class, 3IATLAS passes Jupiter. Its jet gradually fades as the object recedes, and no captured fragment is found. The mystery remains, but it can be pursued within an expanded natural framework. In the other class, a small, new satellite appears where theory insists none should. If that happens, the implication is that somewhere inside the cold, distant body now leaving the solar system, a system existed that could control energy at scales far beyond simple sublimation, adjusting velocity with precision against the pull of a giant planet. Between these two possibilities, the coming months will quietly decide which story the data will allow. As the implications of the energy budget paradox sink in, The discussion surrounding 3IATLAS widens beyond the familiar territory of comet physics and orbital mechanics. A different vocabulary begins to appear in workshops, reports, and quiet exchanges between research teams. Terms that belong to the study of possible technological footprints in astronomy come to the foreground. For decades, the search for extraterrestrial intelligence has focused on signals, on the hope that another civilization might broadcast radio or optical messages across interstellar distances. Alongside that signal-based search, however, another line of thought has developed, one that considers physical artifacts rather than transmissions. In this framework, a civilization that explores the galaxy might send autonomous probes, designed to operate independently for immense spans of time, using the resources of planetary systems to perform scientific surveys or to leave behind long-lived instruments. The theoretical constructs used to describe such probes vary. Some models imagine a single messenger traveling from star to star, performing flybys and sampling environments. Others consider self-replicating devices that use local material to build copies of themselves, slowly filling a region of space. Another class of ideas focuses on sentinels, long-duration observational platforms left in stable orbits around stars or planets to watch and wait. In all of these cases, the probes are assumed to rely on the same physical laws that govern natural objects. They must obey conservation of energy and momentum. They must navigate gravitational fields. They must manage propulsion and power under constraints set by physics. What distinguishes them from comets and asteroids is not the laws they obey, but the purpose of their motion and the internal organization that allows them to act in ways that natural rubble cannot. Against this conceptual backdrop, 3IATLAS begins to look less like an isolated anomaly and more like a potential instance of a broader category. Its behavior in the inner solar system, with a long-lived sunward jet opposing radiation pressure, resembles a form of continuous propulsion. Its spin-axis alignment with the Sun and its low-inclination orbit through the planetary plane give it a geometry that seems optimized for interactions with the architecture of the system. Its projected passage through the outer layers of Jupiter's Hill sphere creates an opportunity to leave something behind in a stable orbit around the giant planet. These features, taken together, align with a pattern that has been considered, in abstract form, in studies of interstellar probes. A vehicle entering a new planetary system might choose a path along the stellar equatorial plane, where most of the planets reside, to maximize the chance of close encounters with massive bodies. It might use low-thrust operations, akin to a persistent jet, to adjust its trajectory gradually, conserving energy while still exercising control. It might target the gravitational domain of a large planet as a location to deploy smaller units, because a captured satellite can remain nearby for geological timescales, using the planet's gravity as an anchor. In such a scenario, a main vehicle could act as a carrier, passing through the system at high speed, while leaving in its wake small, autonomous instruments bound to key locations. The outer regions of a giant planet's satellite system are particularly attractive in this context. They offer long-term dynamical stability, relative isolation from dense atmospheric or radiation environments, and broad views of the host star and inner planets. A small object placed into such an orbit could monitor the system quietly, its signals faint against the background noise of space. Or it could remain entirely passive, storing information for retrieval in some distant future. 3IATLAS, interpreted through this lens, begins to resemble a candidate for such a messenger. It is small enough to be overlooked by casual surveys until it approaches relatively close. Its interstellar trajectory ensures that it is not gravitationally tied to the Sun and can move on to other systems after passing through this one. Its main jet, functioning as a kind of propulsion, appears tuned to maintaining a specific orientation with respect to the Sun, allowing the object to keep its internal systems aligned with a stable reference direction. Its impending skim through Jupiter's Hill sphere offers a plausible opportunity to detach a secondary unit and leave it behind. None of these properties on its own requires an artificial explanation. Even together, they do not constitute proof, but they match, in broad outline, the patterns that theoretical work on interstellar devices has anticipated. This resonance between abstract models and observed behavior is what raises the stakes of the March encounter. The idea of physical technosignatures, observational manifestations of technology, has been explored in many forms. Some researchers consider the possibility of large-scale structures orbiting stars designed to capture energy. Others think about waste heat signatures, where power-hungry systems radiate excess energy in characteristic ways. Still others focus on anomalies in asteroid belts or planetary atmospheres that might indicate industrial activity. In this catalog of potential signs, the arrival and departure of a single small object like 3IATLAS would ordinarily be easy to overlook. Yet, in this particular case, the combination of a physics-defying jet, a statistically unlikely alignment, and a trajectory finely threaded through a planet's gravitational reach marks it out as a candidate for a subtler kind of signature. If a fragment is left behind in orbit around Jupiter, and if the energy budget required for that capture cannot be accounted for by natural processes, then the fragment itself becomes the technosignature. It embodies, in its very existence in orbit, evidence of deliberate manipulation of motion and energy. Discussions of such possibilities are tempered by caution. Astronomy has a long history of encountering phenomena that defy existing models and then, with time and better data, resolving them into natural processes that were not previously understood. Pulsars are discovered as sources of regular radio pulses and are briefly considered as possible artificial beacons before being recognized as rotating neutron stars. Quasi-stellar objects appear as intense, distant light sources and are gradually understood as the cores of active galaxies. Against this history, many researchers argue that extraordinary claims demand extraordinary evidence, and that every possible natural mechanism should be exhausted before considering technological explanations. In the case of 3IATLAS, this cautious approach translates into an intense effort to model every aspect of its behavior within natural frameworks. The jet is examined as a potential manifestation of extreme anisotropic outgassing from a fractured interior. The spin axis alignment is explored as the product of rare but conceivable sequences of torques and collisions in its home system and along its interstellar journey. The trajectory through the ecliptic plane is treated as an outcome of random injection among a vast population of interstellar bodies. The Hill-sphere encounter with Jupiter is framed as a coincidence that happens to align with these other features. Even when these natural explanations are stretched to their limits, they remain part of the discourse, because the alternative requires accepting that an artifact of unknown origin is passing through the solar system in the present epoch. Yet the same caution that urges restraint also demands honesty about where natural explanations fail. The energy budget paradox is one such point of failure. The persistence and directionality of the sunward jet push against the boundaries of current comet physics. The combined geometrical alignment of spin axis and orbital plane strains the assumption of randomness. The potential capture of a fragment by Jupiter, if it occurs, would drive the system beyond what thermal outgassing, tidal disruption, or three-body gravitational interactions can plausibly accomplish under the specific conditions involved. In this sense, the technosignature framework does not replace natural explanations. It stands ready to be invoked only if the data insist. It offers a structured way to interpret a class of outcomes that otherwise lack a coherent natural narrative. If 3IATLAS behaves in all respects as a strange but ultimately natural comet, then the technosignature framework recedes. If it leaves behind an object in orbit that should not be there, that framework becomes central. The consequences of such a shift would be profound. A captured fragment around Jupiter, identified as a potential artifact, would change the search for evidence of other civilizations from a speculative exercise to an empirical science grounded in a particular accessible example. Telescopes could probe its spectrum, looking for metallic or synthetic surfaces. Radar could, in principle, map its shape. Space agencies could plan missions specifically to visit it, sending probes that would cross the gulf between supposition and direct inspection. Even if such follow-up remained technologically or politically difficult, the very existence of the object would demonstrate that technological activity has occurred within the solar system at least once from an external source. It would imply that the galaxy contains actors capable of building machines that cross interstellar space and operate autonomously for long periods. In the absence of such a captured fragment, the status of 3IATLAS would remain ambiguous. Its jet, its alignment, and its path would still demand explanation, and they might drive innovations in the understanding of cometary physics and the structure of interstellar remnants. Perhaps new models of internal composition or thermal evolution would emerge, showing how pockets of supervolatile material can produce long-lived, narrow outflows. Perhaps more sophisticated dynamical simulations would reveal ways in which spin axes of interstellar bodies can be shepherded into special orientations through sequences of interactions more complex than currently considered. In that outcome, 3IATLAS would still be one of the most peculiar small bodies ever observed, but it would remain within the expanded boundaries of natural phenomena. Between these two futures lies the encounter with Jupiter's Hill-sphere. In anticipation, the narrative around 3IATLAS splits into parallel threads. One thread continues to refine the physics of jets, alignments, and orbital dynamics, aiming to make the natural explanation as strong as possible. The other thread explores the implications of a positive technosignature, outlining what it would mean if the object behaves in ways that only technology can account for. Both threads converge on the same observational test. They await the same data. In the background, a broader philosophical shift takes place quietly. The idea that interstellar probes might be present in planetary systems has always been abstract, a subject for equations and thought experiments. 3IATLAS turns that abstraction into a concrete case with dates, coordinates, and measurable consequences. It anchors speculative frameworks to a particular trajectory and a particular gravitational encounter, inviting the possibility that questions once asked in general terms about advanced engineering in the galaxy may soon be examined in a specific context of a single, small body and whatever it may leave behind as it crosses the realm of the giant planet. As March of the year 2026 approaches, preparations across the astronomical community converge on a single, narrow window of time when 3IATLAS will cross the outer reaches of Jupiter's Hill sphere, and the emphasis shifts from theory to observation, from modeling what might be possible to arranging instruments so that any sign of what actually happens will not be missed. Space agencies and observatories begin to treat the encounter as a quiet but high-value experiment, one that cannot be repeated. At NASA, planners responsible for the Juno spacecraft, which has been orbiting Jupiter since the year 2016, review the spacecraft's trajectory and instrument capabilities in light of the projected passage. Juno does not come physically close to 3IATLAS. The distances involved are immense, and space remains overwhelmingly empty. Yet, proximity in space is not only measured in direct separation. Juno is embedded deep within Jupiter's magnetosphere and charged particle environment, sensitive to changes in the plasma and fields that envelop the planet. If 3IATLAS executes any energetic maneuver or sheds material in a way that interacts with the Jovian environment, there is a chance that Juno's instruments could record subtle signatures of that disturbance. The team examines the capabilities of the WAVES instrument, designed to measure radio and plasma waves in the magnetosphere, and of the magnetometers that trace variations in the planet's magnetic field. They consider whether a sudden burst of high-speed particles or a transient plume of ionized gas, if it occurs near the Hill sphere boundary, could propagate inward along field lines or through the solar wind and leave a detectable imprint in the data. Schedules are adjusted so that Juno devotes as much observing time as possible around the predicted encounter period, within the constraints of its existing orbit. At the same time, Juno's camera system, although not able to resolve a distant object as small as 3IATLAS directly during the passage, is tasked with surveying the outer space around Jupiter in the weeks and months afterward, searching for any new, faint point sources that move against the star background in a way consistent with a newly captured distant satellite. On Earth, large optical and infrared observatories organize coordinated campaigns. Deep imaging of the relevant region of space near Jupiter's projected position is carried out before the encounter to establish a baseline, mapping every detectable object down to the faintest limits. This reference catalog will later serve as a comparison set against which post-encounter images can be matched. Any new point source appearing in the relevant region, particularly one that shows the slow, looping motion characteristic of a distant Jovian moon, will stand out against this backdrop. Wide-field survey telescopes are particularly important here, because the outer Hill sphere spans a broad swath of sky, and a small new satellite could appear anywhere within that zone. Astronomers design observing sequences that balance depth and coverage, exposing long enough to detect small bodies, but scanning large enough regions that a fragment is unlikely to slip through unobserved. Radio observatories also take their place in the network of watchers. Arrays that monitor the sky for transient radio bursts, normally focus on phenomena such as solar storms or distant explosions, are alerted to pay attention to the sector containing Jupiter during the critical days. If 3IATLAS performs a high-energy event, expelling ionized material at great speed, there is a possibility that the resulting interaction with the solar wind or Jovian magnetic field could generate radio emissions, brief and faint, but potentially distinguishable against the usual variability of the environment. Data archives are prepared to tag and preserve any such anomalies for detailed follow-up. Beyond NASA, other space agencies adjust their own platforms. Space-based observatories in Earth orbit or at gravitational balance points are tasked with monitoring both the interstellar object itself and the region around Jupiter. Imaging instruments capable of precise tracking are used to refine the orbit of 3IATLAS as it approaches the encounter, narrowing uncertainties so that the timing of closest approach to the Hill sphere and the best locations for post-encounter searches are known as accurately as possible. Spectrographs are trained on the object during its outbound leg prior to the Jovian passage, seeking any changes in the composition or velocity structure of the coma and jet that might hint at preparatory activity, such as variations in jet strength or shifts in the directionality of outflow that could foreshadow a more dramatic event. Coordination between teams becomes crucial. Because no single instrument or observatory can cover every aspect of the encounter, the observational strategy relies on layering multiple, complementary perspectives. Some facilities focus on the fine details of 3IATLAS itself, tracking the behavior of the sunward jet, measuring changes in brightness, and guarding against any unexpected fragmentation that might occur even before Jupiter's influence becomes significant. Others concentrate on the broader environment, scanning for new objects in orbit or for signs of large-scale disturbances. Regular teleconferences and data-sharing agreements allow rapid cross-checking. A sudden flare in one observatory's data can be correlated with subtle shifts in another's. An apparent new point source near Jupiter can be compared against orbital predictions for fragments to assess whether it could plausibly be linked to the interstellar visitor. In the background, statistical analysts refine the predictions for what a captured fragment would look like. Given the incoming trajectory of 3IATLAS, its speed, and the geometry of the Hill sphere passage, they compute the range of possible orbits for any fragment that might be shed and successfully captured. These orbits are not arbitrary. They will tend to lie in planes related to the original path, with specific ranges of semi-major axes and eccentricities. By compiling this family of potential orbits, observers gain a template against which real detections can be compared. A new object discovered after the encounter that follows one of these predicted paths would be an immediate focus of attention. Conversely, small bodies whose orbits clearly fall outside this family can be quickly classified as unrelated background satellites. Consideration is also given to the possibility of negative results. Experienced researchers emphasize that an absence of evidence is not always evidence of absence. It is entirely possible that 3IATLAS will pass through the outer Jovian system without shedding any large, long-lived fragments, either because no such fragments exist or because any released material is too small or too faint to detect with current technology. To guard against premature conclusions, detection limits are carefully quantified. For each telescope and observing campaign, teams compute the smallest and faintest object that could be reliably seen at various distances from Jupiter. These limits form the boundaries of the test. If no new object is found above these detection thresholds, then strong constraints can be placed on what, if anything, was left behind. If a new object is found, its brightness and motion can be measured against the same limits, allowing an estimate of its size and orbit. Within control rooms and data centers, there is an undercurrent of quiet tension. Publicly, the encounter is often described as an opportunity to study an unusual interstellar comet as it brushes past the largest planet in the solar system. Internally, among those most familiar with the full constellation of anomalies associated with 3IATLAS, the language is more precise. It is recognized that the upcoming passage offers a rare and possibly decisive discriminant between broad categories of explanation. The assets now in place, from Juno in Jupiter orbit to the network of Earth-based and space-based telescopes, represent a level of preparedness not available during earlier encounters with anomalous objects. Previous interstellar visitors came and went quickly, discovered only after they had already passed perihelion, with limited time to respond. In this case, the key phase has been anticipated months in advance, and the observational infrastructure has been mobilized accordingly. Each team, however, also understands the limitations of its tools. Juno's instruments are sensitive but local, probing the environment near the spacecraft rather than the distant outer boundary of the Hill sphere. Ground-based telescopes must peer through Earth's atmosphere, which imposes noise and limits resolution. Space-based observatories offer clarity but have narrow fields of view and finite observing schedules to juggle. Within these constraints, the aim is simple: record whatever happens with as much fidelity as possible, so that the story 3IATLAS writes in its passage through Jupiter's domain can be read in detail afterward. As the projected date nears, the flow of data from 3IATLAS itself is watched carefully for last-minute surprises. Any abrupt change in the jet, such as a sharpening or weakening, any sudden brightening that could signal internal restructuring, any shift in the measured non-gravitational accelerations that might indicate a change in thrust-like behavior would be scrutinized in real time. These variations, if they occur, could signal preparations for a major event, or simply mark the final stages of a natural evolution as the object recedes from the Sun and its activity declines. Either way, they would influence how the subsequent encounter is interpreted. The sense builds that the solar system has prepared, almost by accident, an array of eyes and instruments at the finish line of an experiment that no one deliberately set up. 3IATLAS, with its defiant sunward jet and improbable geometry, is the moving component. Jupiter and its vast invisible hill sphere form the static apparatus. The physicists and astronomers, dispersed across the planet and in orbit around another, are the recorders. When the object threads the edge of the giant's domain, whatever takes place will be captured in a collection of images, spectra, and field measurements. Later, those records will be sifted for signs of either a quiet passage or a departure marked by a new gravitational resident. In that distinction lies the next turn in the narrative of 3IATLAS, one that will either deepen an already complex natural mystery or open the door to the first direct evidence that a technological artifact from another star has passed through and acted within the solar system. In the final days before the encounter, the narrative of 3IATLAS condenses into a quiet tension that runs beneath routine operations and scheduled observations. The object itself continues outward on its predetermined path, a small, distant source in the sky, whose light curves and jet profile are now familiar. The sunward beam remains present in the data, still narrow, still oriented along the line to the Sun, within small fluctuations. Activity has declined somewhat compared to the peak near perihelion, as expected for a body receding into cooler regions. Yet the fundamental characteristics of the jet and the spin state persist. This persistence reinforces the sense that whatever internal configuration drives the outflow remains intact, at least for now. In observatories distributed across the globe and aboard orbiting platforms, preparations settle into a pattern of waiting, punctuated by calibration and rehearsal. Instruments are tested, acquisition scripts are refined, and reference fields are rechecked. Teams run through the same planning sequences, verifying pointing coordinates, exposure times, and scheduling windows. Among those closely following 3IATLAS, a dual awareness emerges. On one level, the encounter is simply another observational campaign, one more entry in the long record of coordinated efforts to study celestial events. On another level, it is a boundary test for current understanding. A moment when the combination of anomalous data and unusual geometry could either be folded back into a broadened natural framework or force a step into a domain where technology from elsewhere must be considered. This duality informs the way expectations are framed. No one can guarantee that any decisive signature will appear. The most probable outcome, given the harsh constraints of detection limits and the enormous distances involved, is that no clear evidence of a captured fragment will be found. In that case, the story of 3IATLAS will still demand explanation, but the urgency of technosignature interpretations will soften. There will still be a physics-defying jet to understand, a statistically unlikely alignment to account for, and a carefully threaded path to model. But the lack of a new gravitational resident around Jupiter will keep the discussion anchored more firmly in the domain of extreme natural behavior. At the same time, the community must be prepared for the less probable but more transformative alternative: the detection of something tangible left behind. Analysts outline the range of observational signatures that would move the discussion from speculation to strong inference. A newly detected distant satellite of Jupiter, whose orbit can be traced back to the March passage of 3IATLAS, would be one such signature. Another possibility, more subtle but still suggestive, would be the detection of a brief, intense disturbance in Jupiter's magnetosphere or surrounding plasma, coincident in time with the predicted Hill-sphere crossing, indicating a large, directed release of energy from the interstellar object. Either outcome would challenge established models. The hours surrounding the encounter pass without spectacle. In the data streams flowing to Earth, no obvious bursts or flares announce that a crucial moment is unfolding. From the standpoint of an observer on the ground, nothing changes in the sky. Jupiter continues its slow progression against the stars, and 3IATLAS remains far too faint for unaided perception. The event exists primarily in numbers, timestamps, coordinates, predicted relative velocities, and the quiet hum of telemetry as instruments log their measurements according to plan. Even this uneventful passage carries weight. It embodies the principle that decisive tests in science are not always heralded by striking visual phenomena. Sometimes they consist of careful before and after comparisons, of patient scrutiny for small differences that might mark the signature of a process otherwise invisible. In this case, the decisive evidence, if any, lies not in a dramatic display, but in whether the orbital ledger of the Jovian system changes by even a single entry. As post-encounter weeks unfold, the analysis enters a new phase. Deep images taken after the passage are aligned with pre-encounter frames and subtracted. The process is meticulous. Slight differences in seeing, noise, and background illumination are accounted for. Known Jovian satellites, foreground stars, and background galaxies are all matched and removed from the comparison. The residuals are examined for any remaining points of light that cannot be associated with previously cataloged objects. Simultaneously, orbital data for known distant Jovian moons are rechecked. Any deviations from predicted positions are assessed to see whether they can be explained by measurement errors, by previously unmodeled perturbations, or by the presence of an additional body. Juno's data are downloaded and sifted. Magnetometer traces are inspected for unexpected spikes or perturbations. Plasma wave spectra from the critical period are searched for transient features that could indicate the passage of an energetic disturbance. Any anomalies are cross-correlated with solar activity records because solar flares and coronal mass ejections can also drive sudden changes in the Jovian environment. Only those disturbances that cannot be tied to solar sources or to known internal Jovian processes are set aside for closer scrutiny. Through all of this, the possibility remains that the encounter has left no detectable trace. Even if 3IATLAS behaves in a manner consistent with an engineered system, it might choose not to deploy anything at Jupiter. Or it might deploy something so small and so faint that current instruments cannot see it. Conversely, a new distant Jovian object, if detected, might eventually find a natural explanation rooted in complex gravitational histories or in previously unrecognized populations of small bodies. The data alone, however precise, cannot easily distinguish intent from coincidence. What they can do is constrain the space of plausible narratives. If no new object is found above the detection thresholds, then any hypothetical technologies associated with 3IATLAS must have chosen outcomes that leave no large physical markers in the Jovian system. In that scenario, the jet, the alignment, and the trajectory still demand interpretation, but they can be addressed as parts of a broader effort to understand the spectrum of natural behaviors among interstellar bodies. If a new object is found whose orbit strongly suggests release from 3IATLAS during the Hill-Sphere passage, then natural narratives must contort around the energy budget paradox, invoking processes that have never been observed and that strain known physics. The strength of the technosignature framework, in that case, would rest on its ability to accommodate the full set of constraints without such contortions. Regardless of the specific outcome detected, the passage of 3IATLAS leaves a lasting imprint on scientific thinking. The very act of treating a small, interstellar object as a potential carrier of technology changes how future discoveries will be approached. Survey programs that scan the sky for moving objects may, from now on, not only flag unusual trajectories and brightness variations, but also assess whether any incoming body exhibits combinations of features analogous to those of 3IATLAS. Persistent non-gravitational accelerations, statistically unlikely spin alignments, and paths that intersect the gravitational domains of major planets in ways that enable long-term capture. Missions planning might adapt as well. Spacecraft designed to visit comets and asteroids could include contingency plans for rapid retargeting if an interstellar object with unusual characteristics is discovered on an accessible path. Observatories that primarily study natural processes could incorporate technosignature diagnostics into their data pipelines, recognizing that the same measurements used to understand jets and orbits can also, under the right circumstances, serve as evidence for controlled motion and engineered behavior. 3IATLAS also reshapes the relationship between the search for distant transmissions and the search for nearby artifacts. The traditional emphasis on listening for deliberate broadcasts assumes that other civilizations choose to announce themselves through beacons or messages. The possibility that such civilizations might instead, or also, rely on quiet physical presence in the form of probes or monitors shifts some of the attention toward local space. A single small object passing through and possibly interacting with a planetary system becomes not merely an astrophysical curiosity, but a potential example of a communication strategy that does not prioritize obvious signals. In this light, the solar system appears not only as a place to listen outward, but also as a place to look inward, scanning its own structures and peripheral regions for signs that travelers from elsewhere have passed through before or left markers to be discovered. The narrative of 3IATLAS reinforces a methodological principle. Even in the face of intriguing coincidences and suggestive behaviors, restraint remains essential. Every step toward interpreting the object as a technological artifact must be supported by specific, verifiable observations. The temptation to fill gaps with stories that exceed the data must be resisted. At the same time, dismissing anomalies simply because their implications are uncomfortable would be a failure of inquiry. The balance lies in a disciplined openness, willing to expand the catalog of natural processes where new mechanisms can be justified, and willing to consider technological explanations where energy budgets, geometries, and outcomes categorically exclude known natural pathways. In the end, 3IATLAS stands as one of the most anomalous small bodies ever observed. The persistent sunward jet, the improbable alignment of its spin axis with the Sun, the low inclination orbit through the planetary plane, and the precisely timed passage through Jupiter's gravitational boundary form a pattern that refuses to be entirely absorbed by existing models. Whether or not a new Jovian satellite ultimately appears in the data, the object has already altered the landscape of thought. It has driven the refinement of observational strategies, the development of new theoretical frameworks, and the integration of technosignature concepts into mainstream dynamical and cometary studies. It has turned abstract questions about interstellar probes into concrete analyses with dates and velocities. The encounter with Jupiter's Hill sphere, quiet as it is in visible spectacle, marks a boundary in understanding rather than a dramatic event in the sky. On one side of that boundary lies a universe in which all small bodies, however odd, are assumed to be the product of natural processes until those processes are exhausted. On the other lies a universe in which at least one small body must be treated as a candidate artifact, its trajectory and behavior read not just as the consequence of gravity and ice, but as the potential expression of design. 3IATLAS hovers between these two universes, its true nature unresolved. Data gathered during its passage will continue to be analyzed, reanalyzed, and contrasted with future discoveries. Perhaps, in time, another interstellar object will arrive with similar features, strengthening the case for a class of technological messengers. Perhaps new physics will emerge that explains the anomalies in a way that preserves a purely natural narrative. For now, the mystery remains open. A small interstellar traveler has crossed the solar system, defied expectations near the Sun, aligned itself in improbable ways, and threaded the gravitational reach of the largest planet. What, if anything, it has left behind will shape how this story is ultimately told. But even in uncertainty, the object has already done something remarkable. It has forced a planetary civilization to examine its own assumptions about what moves among the planets and why, and to consider that the sky overhead might contain not only debris and ice, but also, perhaps, the quiet passage of intent.